Okay, so what do we have today? PCA part 2. And I'll show you something on the last half hour of the class. Before I start, about PCA, have you seen this book? You guys have seen this book? Linear Algebra and its Applications? No? Yeah, if you haven't seen this book, you have absolutely must read this book, okay? So all this PCA, linear algebra, decomposition, how it works, eigenvectors, eigenvalue, determinant, sigma, sigma minus 1, all this stuff. This is a very introductory book. It's supposed to be first year college in math. So the people who go to college in the first year, right, they're 19 years old, they take a course in linear algebra based on this book. It's the kind of book that you should be able to read most of it in the train while you take the train home. And some of it, maybe 20%, will require some pen and paper at home. It's a fundamental book in mathematics, the whole linear algebra thing. So if you have not seen this, you absolutely must do it. There's another one for probabilities. It's called All of Statistics, pink book. That's the one that you have to read for basic intro to probabilities. That is assuming you have not done a linear algebra course in your college. If you've done, you probably know everything already. But even then, I think it makes sense to take it in the train with you and read just to recap things. So PCA part 2, let's see where we were last time. So the bigger chapter is dimensionality reduction, right? And now we do PCA, which is like the basic version of dimensionality reduction. Most people, when they want to try a simple thing, they do PCA for dimensionality reduction. So our purpose is to get from D dimension, which is the original space, into much fewer dimensions. But not at random, right? We want to preserve something, right? What do we want to preserve? So it's not like, okay, take the data, transform it from 784 dimensions. Remember, what data was that? MNIST. We can transform it in 3 dimensions very quickly. We take every image and say, assign 3 random coordinates to it, right? And now we've got ourselves 70,000 random points in 3D. That is a reduction from 784 to 3, but not very useful because now those are 70,000 random points. They're not corresponding to the original points. So we want to reduce dimensionality in a way that preserves somehow the data properties. So get from D to some, this is the original D, presumably big, to a D that is small. Like for example, from 784, I get to 20 maybe. Or if I'm more aggressive, maybe I go to 3. I don't know. But we want to preserve data properties. It's easy for me to say data properties, but it has to be more specific than that. What do we actually trying to preserve? This is a massive, massive field of study in data science, machine learning. I cannot emphasize enough how much people knew about this problem for 40 years, and they thought, you know, we have PCA, we have this and that. Only recently, last 10 years, people have realized we are very bad at dimensionality reduction. Extremely bad. Because what we really need to do in terms of the goal, it's very hard. There's new fields called multi-dimensional scaling and non-negative matrix factorizations, stuff like that, that movie recommendation are using. Those are extremely hard mathematical problems. Sometimes they're called embeddings. That's the same like dimensionality reduction. Embedding means how do I place my data points in a new space, embedding in that space. So the problem is what we really want to do is very hard. And what we can do is not that useful. So we have this dilemma. We can, okay, we want to preserve the order of, in order which you like the songs. You have a bunch of songs. Everybody has songs. There's millions of songs around. Everybody has preferences. We want to reduce the song dimensionality to preserve those preferences. That's hard. We don't know how to do that. There's people at Spotify right now, which I consult with, that are trying to do this. How do we reduce the song's dimensionality in preserving people in list orders? Not an easy problem. But what we can do very easily, that's why we teach it in class, because it's easy. It's PCA, right? Very easy. PCA runs extremely fast, right? But it's not that good. It doesn't do what we really want. So as a story, I'm gonna give today a story, and then as we move on to next week, we're gonna try to complicate things a little bit to see how far we go with that. Like we're gonna say, okay, instead of using PCA, which is kind of a dumb way of dimensional reduction, what about if we use a neural network, for example? Set up a neural network, try to do what's called an autoencoder. An autoencoder also does, in a sense, dimensional reduction. It takes the data in 784 dimensions, encodes it in fewer dimensions in such a way that it preserves some property at the output of the network. So we're going to try to set this up, a TensorFlow neural network. That's your homework for the Christmas break, spring break, is to set up TensorFlow so after the spring break we can run it to do all the encodings with it. But there are many ways to think of dimensionality reduction for a certain purpose. Most of them are difficult. So PCA, let's finish this up. First of all, we had this nice picture here. Here's my data. And I'm going to do it 2D here, because my board is 2D. So this is kind of x1, dimensionality 1, right? So this is the first coordinate, this is x2. And this a point, any point here is a particular xi, right? Which is, in my drawing, it'll be an x1, I, and an xi2, right? Two coordinates. And what I want to say, I have this line E. That's what we did last time. We have a line E. E is just E has norm 1. So E is a unit vector that is the line direction. Because E gives the rotation of the line, right? So we can imagine E being a unit vector right here. And that's essentially the direction of the line, unit 1. What we already said, and I said I let it as exercise, the mean of the data, mu, so this is the mean of the data. We believe this line E, the best line E that we have, passes through mu. Anybody prove that? That the best line there was an objective here, right? So what was the objective? First of all, every xi projects onto the line into something that we call xi bar, right? So the xi bar is the projection or map of xi to line E, right? And then the way we represent xi, we say it's mu plus a vector, right? So we say this is gotta be mu, which is already on the line, plus some units times the E vector, right? What's E times A? That doesn't matter. This is, A is a scalar, it's a real number, and E is a vector. So in other words, let me put mu somewhere to be more clear what I'm doing here. While we're saying every xi point on the line, it's mu plus a bunch of units, which is ai, times the unit vector, right? It's necessary to multiply with E to make sure we stay on the line, right? If I just say plus ai, it doesn't make sense. This is a vector. I can't add a scalar to it. And I have to say add times the direction. I want to move, this is the number of units I'm moving, and this is moving on that direction on the line. And if I want to go on the other side, ai will be negative. Good. So that's what we had so far. And we want to say the objective was to minimize the sum for all i's between xi minus xi bar squared. Right? We want to minimize, which one is xi minus xi bar squared? Is this distance, right? This is a sum of square error, right? Sum of square error or square loss error. Many algorithms and regression that derivates this minimum to obtain the regression line, right? Regression is not, I don't have labels here, I have a bunch of features. Regression is typically between the feature space and the labels, right? That's how regression works. It tries to correlate the feature space with the labels. This is not that problem. We don't have labels here. We're going to use the MNIST as an example, but we're not going to look at the labels, which is going to say 7,000 images, 784 images. Now intuitively, so that's one objective. Another possible objective is to, since we know the mapping is going to be on a line, we need to find two things, right? What's the line and what are the mappings? Remember we did this last time. We said there's two problems here. Which line do you pick? And once you pick a line, where xi goes? Intuitively, it goes like perpendicular. Because once I fix the line, to get the smallest distances from everyone to some point on the line, the smallest distance is going to be the projection, right? So you can make a note here, if E is fixed, right, then the smallest minimum of xi minus xi bar means xi bar has to be the projection, geometric projection of xi on E, right? I think everybody can see that once the line is fixed, the minimum distance from each point gotta be the perpendicular, right? So I think projections so that's one thing. The other thing that we did is mu has to be on the line. That was exercise. In other words, any line that doesn't pass through mu, this is mu. If I take that line and move it to mu as in parallel, I'm shifting it. I'm not changing its direction, right? I'm just taking the line and move it to mu. That's going to decrease the sum of squares. The easiest way to see that is say here's the line. I have a bunch of projections, right? From my points. Suppose my mu is not on the line. Suppose my mu is here. That's the average. This is 1D. Every point here has one feature, one coordinate, right? And this is my mu. So if I pass the same line to mu, I can prove now that the projections of all these points, not to the original line, but to the new line, which because they're parallel, some of them will be shorter, some of them will be longer, right? We can easily prove that the new line passing through mu minimizes, does a better job with the minimum squares in here than the original line. So that's the exercise you guys had. That if the line doesn't pass through mu by moving on mu without changing its direction, that's a better projection line. Okay. here's another objective. I want to maximize the variance, or in English, let's call it spread, of the projections. Those are the xi bars, right? So what I want to do is to say, one way to think about it is to minimize this, because if I minimize the distance, I can think of this as some sort of error, like this is where the point was, this is where it's going to be after the projection. I want to be close to where it was. Another way to think about it is when I look at my maps, my mapping, all the points are going to be on this line, right? Once I'm done projecting things, everything is going to be on this line. Why would I want to have points spread out? An extreme example, if I pick, here's my points, right? They are collinear. I can pick a line like this, and when I project them, they kind of get spread out. That's actually the maximum spread I could get. Or if I pick a line like this, when I project those points, they all get projected to one point. Why the one that has a better spread is better for me? What's the intuition that says, when we look at this line, we take the projections, we want the line that maximizes the spread of the projections, or the variance, right? Variance, it's a notion of how spread the points are. So we don't like a line if the points look like a kind of like they have a long dimension. We like the line that goes along that long dimension because it's going to spread out the projections, as opposed to the other direction, which is going to compact the projections. So what's the intuition? Why we want large projections?
It's because we can model the data better.
Right. It's because as a data representation, the more spread it is, the more information I can capture, right? If I represent everybody with 1 point, extreme example, then I get the mean maybe represented correctly, but that's it. Everybody is mapped to that 1 point. Okay. So I think we proved a bunch of things last time. I don't want to do those proofs again. So we look at the sigma was the covariance matrix, right? So don't be confused between these. I'm going to put those little edges here for sigma, and I'm not going to put them for the sums to make a distinction. This is the sum for all data points xi minus mu times xi minus mu. So I have to put the transpose somewhere. This is a d by d, right? Matrix. So this has to, the original xi is where does the transpose go? So I have a sum. This is a sum of matrices. It has to be d by d, which means every one of these matrices has to be d by d, right? This in here is a matrix. So to this vector is what? 1 times d, right? It has 1 row, right? An xi is a row like that with d columns. 1, 2, up to d, right? So 1 xi is a 1 times d row. The mean is the same. So 1 times d times 1 will be 1 times 1. That's no good. I need the other one. So if I transpose the first one, now I get d times 1, 1 times d, d times d. I sum up, this is a sum from 1 equal 1 to n, right? For each data point, I get the covariance matrix. So sometimes we put a transpose wrong, but if you understand the meaning of the computation, you know where the transpose has to go. If somebody takes the x, some people consider x backwards. It's like the columns are the points and the rows are the features, right? And then d by n, then the transpose will go on the other side. It's no big deal. So to make it clear why this is a covariance matrix, for people who remember covariance all the way from high school, this is, how does this look? If I really want to play with this as a big matrix. Let me put this here. Exercise mu belongs to the line. So this is a d by d, right?
Yes.
So what's on the first? What's in here? The first element of this matrix. So it's a sum of matrices, which means every cell in it, it's a sum. Right? So this is going to be a sum for I equal 1 to n. But who's going to be in this first element? Every one of these terms produces a d by d matrix. So who goes on the first cell in each matrix? It's x, I1, right? 1 meaning component 1 or attribute 1 or coordinate 1, right? Minus mu 1 times xi1 minus mu 1. When I put the exponents once, I don't mean square or cubes. I mean it's a vector. The first component is 1, second component is 2, dth component is d. When I put the numbers down, that's indices. I say data point 1, 2, 3, 4. So my feature, my matrix here, every xi is going to be an xi1, xi2, up to xid, right? And this is x1, and this is xn, the vector. That's my data matrix. So isn't this exactly the empirical variance for what? For first column, right? If I look at this first column, which is the first attribute, maybe that's blood pressure or age or salary, right? Across all the data points I have, what is the empirical variance? If I just want to compute empirical variance. I give you a bunch of values, right? I'm only looking at one attribute across all the data. I will sum what? The values xi1 minus the expected of that, right? Which, of course, the expected of that is exactly the first component of the mean.
Yes.
I sum up those things squared, and that's the empirical variance. I think I have to divide by something, right? N minus 1, maybe. I don't put the n minus 1 here because that's, for everybody. So that's just a number multiplied with the whole matrix. So what is going to be then, say here? What am I going to have here? Actually, let's do the end of the diagonal. That's going to be easier. This is easy. This is every one of the diagonal is just going to be the variance of that column, right? If you look at this, this is going to be I equal 1 to n, right? Who? xi d minus mu component d squared. So that's exactly the variance of the last feature across all the data points, right? That's the variance of this column here. So who's going to be here in this corner? It's going to be a sum from all the data points. All these cells are sums for all the data points. So all the data points of what? X I 1, right, minus mu 1 multiply with xi d minus mu d. So it's the sum of these products over all the data points. But what is this? This is the empirical covariance between what there's two vectors, right? Between column 1 and column D. Right? You look at empirical covariance, you subtract the mean from one, subtract the mean from the other, do the product, and see what you get. Right? That's the covariance between two features, right? So if those features are independent, we expect their covariance to be 0, right? So similarly in here, what we're gonna have? In here it's gonna be the same, is the sum of xi d minus mu d times xi1 minus mu 1. It's no surprise that those are the same because this matrix is symmetric. The covariance between 1d is the same as the covariance between d and 1. Right? So this is the empirical covariance matrix, which is approximatively the same as sigma, right? That's why it's called empirical covariance. It's how we estimate covariance from data.
I don't understand why there is a square in the last one.
Well, it's the same like in here.
Yeah, but for the first term, shouldn't it be a constant instead of from I equal to 1 to n? So for first example, we have taken just x1 to the 1. So how can we take xi to the d for every I value?
So these and these are the same things.
Yeah.
This is for the first column.
Yeah.
This here is for the last column. They do the same exact thing. This is the variance on the first column of data. This is the variance on the last column of data, column D. The only difference is I wrote it as a square, because this is a square, right? It's multiplied with itself. What is the variance formula of a random variable? The random variable that I'm going to consider is x1 here. x1 meaning the column 1 of the data. What is the formula? Square. So this is the mean, of course, for that column, right? This is mu 1, because it's the mean for that column. And the expected of squares, computed empirically, is just sum up the squares and divide by how many there are, right? So that's why the sum of squares, it's essentially the expectation of the square value, because empirically I take the sum of squares and I, instead of dividing by n, I divide with n minus 1. You can divide by n if you like. This is a theoretical empirical variance, but in practice, to get what's called an unbiased estimate, it's proven that you better to divide by n minus 1. It won't matter for you guys. This is a pure theoretical exercise. Your n that you have, 70,000, won't matter if you divide by n minus 1 or by n. 70,000 and 70,001 will do the same thing. But for people playing with small data sets, if n is like 12, then divided by 12 or 11 may make a difference. But for data science, it doesn't matter if we divide with n or with n minus 1. Okay, so this 1 over n is the computing the expected average empirically. It takes the average. I'm counting that somehow I'm saying things that you have seen before. Am I right to make that assumption? That we have seen covariances and expectations before, sort of? Right? Okay. All right, so that's the empirical covariance. And what did we prove last time? We did some proofs here. One proof was saying, so last time, let me see. I think there were two proofs that we did. So one, where is this? So one, we proved that if E is fixed, I think I already wrote that down somewhere. If E is fixed, those are actual projections, right? So E fixed, xi bar will be the geometric projection. Now, the geometric of xi on E, right? Geometric projection means what? If you remember geometry, that's xi times E. Remember that? That if we say, okay, take the actual perpendicular line, how do I get this vector? This is the vector xi from the origin times E. So E will give me, that's only true if they're perpendicular here. By multiplying with E, let me see where I've got that. I can't find it here in my notes. So it's actually xi minus mu times e. And part number 2, how to find the best e. That was a little bit more involved. This one is very simple thing. I think we just took what did we do? We just took we didn't take a derivative. You guys have the notes from last time. We were just taking this objective. Let's say the objective here. What are those units on the line E? So for a fixed E, we want to minimize the sum of mu plus AIE minus XI squared, which ends up being, look at the differential. I think we end up being minus sum of AIE times XI minus mu. That's the sum over I. So I skipped the calculation this time. When we took the differential to say what A we want, we got A equal with E times Xi minus M. Is that true? So I have here the transpose. Oh, it's a little bit more. Sum from I equal 1 to AI squared E squared minus 2 of that. That was the actual formula. There's another sum here that doesn't matter. Xi minus mu squared. So what happened? We took the derivative. We got 2AI equal to 2AI, 2E of that. Right? And then we say AI has to be E transpose X minus mu. Each differential will act only on one AI, right? So the other part that we did was that what's the best E? What we do here, we say the objective in E is approximatively, we're not going to do the calculations again, minus E transpose sigma E plus the sum of Xi minus mu. Now, of course, this it's not an interesting term because it doesn't contain E in it. So as far as we're concerned, what's the best E? The best E comes from here, right? This is not going to matter for figuring out E. So there was a calculation that say the objective depends on this. So then we set up the Lagrangian, right? We got E transpose sigma E minus lambda, that's the Lagrangian constant. And this is the constraint. Remember, E has to be just the direction of a line. That means E transpose E is 1. Now we have that constraint. So Lagrangians act that way. It differentiate the objective. This comes from here. I think we want to maximize this, right? So maximize this. So we maximize this instead of minimize E minus, right? And then we've got the solution that says we want the sigma E to be the same as lambda E. sigma E is the same as lambda E. So that means lambda and E are an eigenvalue, eigenvector pair for the matrix sigma. That's why I point out to that book. In that book, there's an entire theory that leads to eigenvalue, eigenvectors. The eigenvectors are very special vectors for a matrix, are the vectors that matrix does not change the direction. Right? I take the vector E, multiply with a scalar, is in the same direction. Scalars don't change the direction of the vector. Usually matrices, when you multiply the vector, they change the direction. But the eigenvectors are the special vectors for which the matrix does not change the direction. So that's, I think, how far we've got last time. It will be extremely easy, say MATLAB. MATLAB is the king of linear algebra out of all languages, to compute the eigenvalues and eigenvectors immediately for a matrix. Also, MATLAB does very fast computation of the covariance matrix. So MATLAB will be the one to use for this kind of computations. Now, what do we do next? So next, I want to make the following observation. I don't find the page. Just a second. So I want to go back to, this is the thing that we use so far. We want to minimize the distances. Right? We keep going at it. We did not do this at any point in time. We keep going by minimizing distances. We show that that means find the best E, that's an eigenvalue, eigenvector of the covariance, and then once you find E, those has to be the geometrical projections on that line. But what about this? What does it mean? Maximize variance of the projections. So what is the variance of the projections? It's xi bar minus expected of xi bar, right? Squared. For simplicity, I want to make the following assumptions. Assume for rest of lecture, mu is 0. This is actually happening. It's not just an assumption. The first thing all those programs do in PCA and linear algebra, they take the data, the whole data x, and transform it into x minus mu. So this is what kind of transformation? If I take, imagine I have the space of the data in multidimensional. What does it mean to make x equal x minus mu? Subtract the mean. Mean is a vector in there, right? Subtract the mean from everybody. What did I actually do with the data? What? Yeah, the new mean is 0, right? Now after this, the mean is 0. But what I did, this is a shift, right? In terms of geometry, we can do rotations, shifts, or other operations, like inversions. But this is simply taking the data and moving it. And now when I move it, its average is mean, change. It moves to the data. So I can move the data everywhere I want until the mean gets to 0. That's what this does. It takes the whole data and moves it somewhere else. It doesn't change any distance between data points, any angles, nothing. It just moves the whole data until the mean becomes 0. So in some sense, this is the same data set. I didn't change anything. I just changed the axis. You can think of data stays where it is. I'm just moving the axis, the x1, x2, x3. I'm dragging the axis so that the center of the axis is now the mean of the data. So data has exactly the same properties as before. Okay? So we can say mean is 0 is going to spare me for writing mu, 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 mu everywhere in here. Right? So this is what? This is the expected of projections. Now, if I do this, what's the projection? This projection was x, what did we say? Xi mu times E. I'm inconsistent. Sometimes I write xi mu times E. Sometimes I write E times xi mu. That's because my notes assume this matrix, but the book I was having printouts here from, it assumes the transpose matrix, the ones that have the rows and columns. But yes.
Is the mean between dimensions or across dimensions?
The mean is a vector, and each component is a mean for one column. So if you take the mean as, where is it written? It's written here. What this is, in fact, is a mu1, mu2, mu d, right? It's averaging the vector, so each component, who is mu2, is the average of all the coordinate 2 for all data points. The averaging works for vectors just like averaging every single component, right? So now who is this if mu is 0? This is just xi times e, right? That's what it is. So if I do that, I get xi e, right, minus the expected value of xi e squared. So that is I think that is, let's see, xi e squared. Because this is 0. Right? The mean, it's the same mean as before, and I just say the mean is 0. Right? The average of the data points projected is still the same average, the same mu, which is 0 now. In fact, this works even if I don't subtract the mean. This would be xi, what was it? Xi minus mu times e, right? And this is going to be mu. So that's going to go out. It's going to get xi e anyway, even if I don't take the mean in the beginning. So now I want to say this is now my sigma has changed too. So my sigma, this matrix here, what happens if I assume the mu is 0? So I do this assumption. Now who's sigma? That was the sum of xi, sum for all data points minus mu times xi minus mu. One of them is transpose. Now of course all the mu's are 0 now. So this is the sum for I equal 1 to n of xi times xi transpose. So that's what I want to say here. This is effectively sum over 1 equal 1 to n of xi times xi transpose, which is the new empirical covariance matrix. I need some ease here. I think it might be backwards here. Maybe the transpose has to go at the end. I'm not sure. So my notes have this equation written with mu in it. I'm trying to take mu out because I say mu is 0. It makes it easier. So what did I do here? I say the expected variance of the projections. Blah, 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 blah. I got to this E. This E, I transform it into a sum. You can say approximative. It's what is the 1 over n here, right? The sum of the squares. And now this, I wrote it as is this true? E transpose sigma E is this thing right here? Why is that true? So who's sigma? Sigma is this thing, right? So what is this? This is a sum n of matrices. This has to be d by d, right? So I guess the transpose is on the other side. Okay? So what happens when I multiply, this is a matrix now, right? It's a matrix that's d by d. When I multiply this matrix with E times this sum, xi transpose xi, and then this is a matrix, right? And I multiply it again with E transpose on the other side. Now this result has to be what? This is a value, right? It's a number. So this is 1 times d times 1. How is this going to work? From I equal 1 to n. The sum, they can take the e on both sides, right? Because I have a sum multiplied with a vector. First I can move the sum over this vector, right? It's a bunch of x's multiplied with the same e. The sum will distribute across these e's. And then I get the sum, I distribute it over the other e. That's going to be the sum from I equal 1 to n of e xi transpose times xi times e transpose. But I think this is exactly this kind of thing in here. You have to know how the transpose work on a product. A B transpose is what? B transpose A transpose. So I think I have the transpose a little bit off. I think this, if I want to write it that way, is sum of I equal 1 to n of, to get this to work, I need E transpose xi, everything, no, I guess xi, E transpose transpose times xi, E transpose, right? Something like that.
Shouldn't the transpose be on XIE?
Yes. I think I messed up the transposes here, but you can fix this calculation. That's saying, the essential part is saying, the maximizing the variance of the projections leads to the same equation that I optimize here. Remember? In here I said I want to maximize this. I was minimizing the minus e sign, and here maximizing the variance maximizes this. This is important for regression too. You should know this fact, that maximizing the variance of projections is the same objective as minimizing the sum of square errors. Right? So that's an important observation that says maximizing variance on projection is same sum of squares. Square errors. By errors here we mean distance. This is the sum of wherever the point was minus where it is now, squared. And this is the variance of xi projections. So that's to show that those two things do the same thing. That's why getting this objective is the same as getting this objective. It also corresponds to intuition. On one sense, we want to minimize the distances, right? That makes sense. We want the points to be as close as possible to where they originally were. The other way is saying, I want to spread them as much as possible. Turns out, geometrically or algebraically, this is the same thing. Now, we're going to get, just for 10 minutes, a little bit into more math, linear algebra. Just for 10 minutes, okay? So I promise this time is the absolute pinnacle of mathematics. I'm not lying this time. After this, it will be less math. We only need it for 10 minutes. So I want to talk about this covariance matrix because it's a very, very special matrix. Where should we do this? Maybe here. So I'm going to keep the covariance definition on the table here, but I'm going to erase a bunch of other things. So the properties we care about, many matrices has eigenvectors. So far we said you want to find the direction to project the data on. There you go. Find the eigenvectors of that covariance matrix. And by the way, if I want to find the second direction, right? I say I projected one direction, that's the best direction. What's the second best direction to project on? What do you think that's going to be? The second eigenvector. So the first one will be the biggest eigenvector, the second one, not the biggest eigenvector, the eigenvector corresponding to the biggest eigenvalue. If I want another dimension, it will be the second eigenvector, which is corresponding to the second eigenvalue.
So if we have higher dimensions, how do we enforce it's aligned, right?
The projections always align. Even in 780. By the way, what I didn't say on the picture is that we're still thinking of this in the original space. So the space is 784 dimension. The line is a line, which is a unidimensional subspace, but it still is 784 dimensions. So if I want another line, I don't want to put that picture back in there. I'm going to draw it here. So I have a bunch of points, right? I say that's my first line. That's the first eigenvector E1. They may need another line. Maybe I want another line. Suppose this is 3D here, right? Maybe 3D. I have points. Maybe I want another line. That's the first one, E1. And now the second one, E2. All these projections are one line. Even though the space is 784 dimensions, each projection is one line. Now what that does, the first projection maps the data the best it can in 1D. The second eigenvector adds the second best projections. They all contribute to minimizing these distances. The more projections I add, the more the xi bar, which is now, so if I use 1e, one dimension, what's the dimensionality of this guy? So this in here is 1 times d, right? This as a vector is 1 times d in that space, but they actually, if you remember, this was ai plus ai times e, right? E1. So all these numbers were really points on the line. Those are the projections on this line. So I represented the data simply as one unit, one dimension coordinate on one line. If I add another line, now each data point will have effectively 2 coordinates. So if I add another line, it'll be 3 coordinates, 4 coordinates, 5 coordinates. The more I add coordinates to these xi bars, the closer they get to xi. That answer the question?
Like when you like take like all the eigenvalues, do you get exactly the same?
Yes. Theoretically, in practice, there's some data problems. Some things are too small, too unstable. But theoretically, mathematically, yes. So the way you have to think about this, to answer, that was an excellent question, by the way. Suppose I look at my space, my points here. That's actually how you should think of PCA from the beginning. What I'm going to do is erase the original axes first. Get rid of them. And say, I don't like those axes because they don't align with the way the data is written, right? In some sense, the data looks long that way, but my axes are not that way. So the first thing, I'm going to get rid of those 3 axes and plot a different 3 axes. Those are the PCA axes. So far, I didn't reduce the dimension, right? I may have 784 axes here. It's just I'm rotating the axis, the axis coordinate system, so that the data aligns better with the axis. I'm not changing the data at all. The data is the same. I'm just taking my coordinate system and saying, instead of being this way, that looks like nice, I'm taking the system and rotate it, maybe put it that way, with a different angle. It's not 90 degrees anymore. Such that this axis, which are still 784, corresponds better to how the points look like. The points, I didn't change at all. I just rotated and moved the axis a little bit. So now this axis, each point has a coordinate on this axis, a coordinate on this axis, and a coordinate on this axis, right? This is after, again, what I did, I have my 70,000 images representing 784 dimensions. I rotated the space, so I have new axis now. Each point has these are not the original pixel values coordinates, are different 784 coordinates. Now, what PCA says, if you only want one, take the best one out of this 784. If you want 2, take the best 2. If you want 3, take the best 3. So we took 1, but we can prove mathematically if we want to further minimize this distance between the points and the original points and the projections. Because if I take one point, this is the original xi, this is one dimension, one axis, the projection, the distance is going to be this one, right? But if I use 2 projections, now xi bar is the combination obtained in 2 projections. We have 2 coordinates. The distance has shrink, right? Let me do this again. I think. Once I have the PCA axis, so PCA axes are the axes corresponding to variance. These are the PCA axes now. What happened to a point here? A point here has a coordinate here, a coordinate here, and a coordinate here, right? If I only take the first axis, that's E1. Those will be the E1, E2, ED. Those are the PCA axes, which don't change the points. It's just using different projections than the canonical original axis. If I take this point as the coordinate, the distance is going to be this. But if I use 2 points, say that's E2 here, this axis. Now, the xi bar, it's going to be formed by those 2 points. And now the distance is smaller. If I use 3 points, now xi bar is going to get closer to xi. And if I use all 784 projections, xi bar is going to be identical with the projection in 784 dimensions.
You're allowing 4 degrees of freedom.
The points are where they are. PCA re-represents them in a different axis coordinates. So they still have 784 coordinates, but not in the original ones, the new ones. And now it's take the one with the highest variance, right? That's in 2D saying, if you have a bunch of points in 2D, and they look like that, right? It says, if I want to choose one of those 2, this is very small variance here, this is a large variance here, I'm going to choose this axis as my representation. Because as far as, if I use both axes, each point is itself. But if I use only one axis, I'm effectively using the coordinates, the x coordinates here. So that's higher variance. So PCA moves from the original coordinates into a variance coordinates, where the one axis corresponds to the highest variance, the second axis, second highest variance, so on and so forth. Yes?
So in the PCA axis, the origin is...
Oh, that's what I'm about to say now. So why is the covariance matrix so interesting? The covariance matrix sigma is symmetric, meaning sigma ij is the same as sigma ji, right? Because the covariance between dimension 1 and 3 is the same as dimension 3 and 1. And also is positive semi-definite. What that means, for any vector z, z sigma z transpose, that would be a 1 times d vector, right? This is a positive value. So those things are, of course, from this book, both of them, right? That's easy to prove. Not the concepts, but the fact that covariance metric has this property, it's a very simple thing. Again, I'm going to say that mean is 0 for simplicity. It can be done with mu, but let's just assume the data has shifted in a way that the center of the data is now the 0. So if sigma is, what did we have? The last sigma in here was this sum, right? I erase it. Is the sum for I equal 1 to n of, what was it, xi times xi, like that, right? The symmetric, I'm not gonna talk about it because it's obvious that symmetric, yes.
So how did you enforce the positive semi-definite constraint? If there are collinear features in the dimensions, then it won't.
So semi has to do with that. If you say positive definite, then that's again it. But if you say semi-definite, then it allows for, that's a border case, you know. So if for any covariance matrix, we can show the positive semi-definiteness, which I'm going to show right now. But if you restrict this to strictly positive definite, then that's a problem. But we don't need to worry about that concept, although if you read the book, you're going to see the distinction between positive definite and positive semi-definite. So for positive semi-definites, we don't have that problem. Here's why. Take z times sigma times z transpose, right? What is this? Well, sigma is sum, again, this is over 1 over n, xi transpose xi, right? Times z transpose. So this sum is over I, can include the z's on both sides. If you have trouble seeing that, a sum of matrices that all multiply with a vector can expand the sum over this vector and over that vector. So this is going to be sum over I equal 1 to n of z xi transpose xi times z transpose. So what's the dimensionality now of this thing? This is 1d, xi transpose is d1, xi is 1d, and this is d1, right? So this is going to be the sum over I equal 1 to n of z, I guess z transpose xi transpose times z transpose, I got it wrong, xi z transpose times xi z transpose. Is that true? So z transpose transpose is z, xi transpose is xi transpose here, xi is xi, and z transpose is z transpose. Now, what's the dimensionality of this vector, xi times z? Xi times z. So xi was what? 1d, and z transpose is d1. So that's a number. This is 1, 1. Right? So it's a number multiplied with itself. This is a sum of square values. Right? Because each one of those is a number, and it's multiplied with itself. So whatever the values are, doesn't matter. It's a sum of something square. Sum of square things is positive. Went too fast. So what this is saying, it's very easy to show that the covariance is positive semi-definite, because for every z, we get this boom. And symmetric, we discussed symmetry already a few times. Good. So we have those properties. That means these two properties. These are very nice mathematical linear algebra properties. Symmetric and positive semi-definite. What it means a spectral decomposition. Call it eigendecomposition. It means the sigma that has these nice properties can be decomposed as eigenvector eigenvector, this is eigenvector 2, eigenvector D, this is a D by D matrix, times a diagonal matrix, which are the eigenvalues. Times this eigenvector transpose matrix. So these and those are transposed to each other. If we call this matrix, C, and this is the matrix D, this is the matrix C transpose. So this is a diagonal matrix. So C is a matrix of eigenvectors, and D is the diagonal of eigenvalues. Now, more matrices can be decomposed this way, but for a matrix that's symmetric and positive definite, to get to this decomposition, although I didn't write it on the board, is only 2 lines. General matrices have a hard time to be decomposed, but symmetric semi-positive definite, very easy to decompose them this way on paper. The semi-positiveness means all eigenvalues are positive. So all these lambdas are positive. And there is another property. The symmetry means that the eigenvectors are orthonormal. Doesn't matter the name. It says the norm of each one of them is 1, and the product on any 2 of them is. That is, if you take an eigenvector, you multiply with itself, you get 1. That's the norm. That's we said that the norm of each eigenvector is 1. But if I take any E1 and multiply with E3, I get 0. So in that sense, these PCA axes are still perpendicular to each other. This E1, E2, E3, they are orthonormal, so they're perpendicular to each other. That's good. I didn't change the system into a weird angle. I just rotated the original system, right? I took the system of coordinates as given to me, and I rotated in a way that aligns better with the data, but it's still perpendicular. So now the coordinates of every point it's still a geometrical projection on this axis, just as a different axis. It's the original system rotated. Good. So finally, the last step in here. I mean, we can show this for fun. This is extremely easy to show that two eigenvectors are we're going to show that lambda E1 transpose, yes, E2 So what I want to do here is to show that two eigenvectors that are not the same, they are perpendicular to each other, which means their product or product is zero. So if I look at this, who is this A? You see what I'm trying to do here? So what I want to prove is that lambda 1 E transpose E2 is the same as E transpose. So what I'm going to do is to show you guys that this transpose is the same as this. These are two different eigenvalues, right? And if I show this, it has to imply, since lambda 1 is not the same as lambda 2, it has to imply E1 transpose E2 is equal to 0, right? Because this lambda 1 times something equal with lambda 2 times something. If lambda 1 and lambda 2 are not the same value, what they multiply with must be 0. Follow me? How many people with me so far? Okay. Well, maybe we need to go home, read those notes a little bit. Well, how do I prove this? Who is lambda 1 E1? This is, I think, remember the properties of eigenvectors with respect to a matrix? When I multiply them with their eigenvalue is the same as multiplying them with the matrix, right? That's the whole point of the eigenvector, that when you multiply the matrix, doesn't change its value. So this is sigma E1, I think transpose, right? Because it's this is lambda E1, right? E2. So this is E1 transpose, sigma transpose E2, which I think is E1 transpose. This in here is sigma is symmetric, right? So sigma transpose is who? Sigma E2. But who's sigma E2 now for the second eigenvector? That's lambda E1 transpose lambda E2. So of course lambda is a lambda 2. So this is a constant. So it's lambda 2 E1 transpose E2, right? Did we follow this thing? So this is saying lambda E1 is the same as sigma E1. That's a property of an eigenvector. Transpose, do the operations here. Sigma transpose, same as sigma. Now sigma E2, now for the second eigenvector is lambda 2 E2. That means lambda 2 times this equal to lambda 1 times this. And that can only happen if the eigenvectors are, the product between them has to be 0. for this, remember these two properties. If you have these properties, a lot of linear algebra becomes very, very easy. In fact, as a recommendation, computation-wise, every matrix that's positive, semi-positive, definite, and symmetric, MATLAB represents it that way to start with. All the operations are done on this form of the matrix. Eigenvectors, diagonal, eigenvectors, transpose. The last thing I want to say before connecting my projector here is who are our projections then? So I'm going to take this P matrix. I want to write this product here as P times P transpose. This, the whole thing. It's very easy to do. This is already the transpose of that. Right? This is C. I call this matrix C. This is C transpose. I need to write it as C times, there's this D in the middle, the diagonal matrix. This is C transpose here. But the diagonal matrix, I think I can write it as some sort of D times D transpose. It's not D, I have to take the square roots of it. Right? If I take the square roots of those lambdas, being a diagonal, it's the same as this transpose, of course. So what I would like to do here is to write the C times square root of lambda 1, square root of lambda 2, square root of lambda D. And by the way, why can't I take the square root of this thing? Because they're all positive, right? They are positive because I have it in here somewhere. So now I put this matrix again, square root of lambda 1 up to square root of lambda D, and times C transpose. So I want the P to be this part, and this here to be the P transpose. That's what MATLAB returns on PCA, this P, which is the eigenvector times, by the way, who do you think lambdas are? Eigenvalues, but they are actually the variances. So square root of lambdas would be? Right? So these are actually the variances for each dimension, lambdas. So now the MATLAB returned this P. So what are the projections going to be? Xi is just xi times this P. Remember we wanted the projections to be xi times E somewhere in here? I think we had it somewhere. Right, so this, I forgot what it is. The projection xi was simply xi times E. Now if I have multiple E's, so that's E1, that's column 1. This way the xi has only one coordinate because I'm taking xi multiplying with an E, right? But if I want another coordinate, I'm going to do the same xi times E2 now. And then xi times E3. And then I get multiple coordinates. That's what happens here. When I multiply with this P, I'm actually getting all the coordinates. Those are not exactly the ones we want because they multiply with the standard deviation values. So if I want to get rid of the standard deviations, I can use P, just the eigenvectors matrix. So if I think about it this way, this is the full projections in 784 dimensions, right? Because P, again, P is a matrix that's D by D. So I'm not changing the dimensionality at all. X was, so without I, this is N by D times D by D. This is the rotation part where it says take the axis, create new axis, right? It's still D by D. How many people with me? So this part, it says take the original matrix, rotate the axis with those eigenvectors. And I'm adding the scaling of lambdas in here because that's what MATLAB does. But if I take the P, just the eigenvectors, I'm only doing the rotation. It's a rotation because it's an orthonormal matrix. When I multiply with data, I'm simply rotating the space around. So now how do I do actually dimensionality reduction? Once I've done the projections, what did we say? We got the whole data set represented not in original axis, but in the PCA axis, which are the variance axis. How do we say, okay, we don't want 784 dimensions, we only want 2?
Select the best two.
Best 2 means what? Which 2 are the best 2? The one corresponding. So assuming I'm sorting the eigenvalues by magnitude, the first 2 columns in this matrix, right? This is who? This is X multiplied with E1 column, sorry, E1, E2, all the way to ED, plus some scaling. This is times lambda 1 times lambda 2, so on and so forth. So if I say just take the first 2 columns, it's X multiplied with E1, that was our first projection, and then X multiplied with E2, that was our second projection. Right? So all I have to do to say here, if I get this P matrix, if I multiply my original matrix with P, I'm doing the rotation of the space. So I get 784 dimensions, but now in a new space that aligns with the variances. If I want to take some of them, not all of 784, but maybe 3 or 4 of them, or 5 or 20, that corresponds to the axes that have now the largest variance. And all that's very easy to do because sigma has such nice properties. In particular, if some lambdas are 0, suppose out of these 784 eigenvalues for MNIST, suppose only 10 of them are non-zero, the other 10 are 0. The other, 774 are 0. What does that mean in data? What happens if 774 eigenvalues are 0? It means there is no variance on those, which means after rotation, that value, pixel value or whatever it is, was constant for all images, was all white. So I can ignore this because they are constant, they have no information in them. So ignoring happens to say, since I multiply with the lambdas, or square root of lambda, these eigenvalues, these vectors are already 0 here, right? So what's going to happen in this matrix once I make the projection, if I have some 0 eigenvalues, those are going to be 0 columns in my projection matrix, right? Everybody that gets a lambda of 0, it's actually a 0 column. And so once I sort them, it's going to be the columns on the right that are 0. So if I have 0 eigenvalues, I can theoretically remove those coordinates, and I have the same matrix effectively. Meaning it's a smaller dimensionality space, but I didn't lose any information. But I don't have 0 eigenvalues. What happens is, the more I remove eigenvalues that are close to 0, I'm not actually losing information, right? Because I know if I remove an eigenvector corresponding to a 0 eigenvalue, that's effectively not losing anything. If I remove eigenvalues that are close to 0 but not 0, I'm losing a little bit. And if I remove eigenvalues that are big, then I'm losing a lot of information. Ideally, I would remove only the 0 eigenvalues, and then I'll just restrict the space to a subspace that has the same properties, but just smaller dimensionality. So, how does this stuff work, actually? See if we can get this done in 12 minutes here. Maybe we need to do some next time. So by the way, how long did it take you guys to do MNIST on the MNIST K-means? If I plug 70,000 images with 784 dimensions, compute distance matrix, then run K-means, how long does it take? Huh? How much time? 2 minutes? To compute a distance matrix and k-means? Let's see what we have here. We have my emails. So what do I have? A is this data. I've read the A directly from k-means, right? Sorry, M is data. So that's A, and then I mean I can load it again, just for you guys. See, that's my data. That's what I loaded, and now I can say x equal. I get data transpose, right? Size of x. What is that? That's good, right? This is integers, so I need to transform it for matrix MATLAB not to complain to double numbers. And then let's run k-means. I don't have a distance matrix. This k-means that I have takes the data transpose, so I have to transpose it. I say k equal 10. Let's see how fast this runs. I hope we can. Oh, it's done. Okay, so that's k-means. Y is the clusters that it's got from k-means of all those images. It's 70,000 IDs, cluster IDs. So now, what I want to get, I have also labels. I'm reading those labels. So I have labels, everybody's actual label. What kind of digit is it? 0, 1, 2, 3, 4. So I'm going to take just in MATLAB here the indices of the data that have label 2. Right? So I'm getting a bunch of them. How many images have label 2? 6990 images have label 2. Now, I want to see how these label 2s distribute over the cluster that I just obtained with k-means, right? So I'm going to say, MATLAB, can you plot for me these y's that I have? Restricted to, in MATLAB, when I say just give me those indices, there's 70,000 y's here. Everybody has an ID, a cluster ID. But if I say just do look at those 6990 images, these indices, I'm restricting the y's to only images that have label 2. So now MATLAB is going to do a histogram of this. I don't know where it went. Oh, here. So what does this mean? It means that across the clusters, those are the clusters, right? 1, 2, 3, 4, 5. I've only plotted images that have label 2. Looks like a lot of images went to that one cluster, which is a good sign, right? It means that if you look at images, all images that are 2s in the data, they all go to one cluster. That's a good thing. I can do this for, say, a different index, 3, right? This is all the images that have label 3. Those are the 3s in the data. So I can do this. Not bad. I mean, not as good as the 2s, I guess, because now they spread over 2.5 clusters a little bit. I can do this for the 7s. So those are just indexes, which data sets have this. Not bad, I would say, for this is a fast k-means implemented by somebody extremely fast in MATLAB. It does the same as the original k-means, just much faster. So you can see the clustering kind of worked. I didn't compute purity here because I'm more interested in see how the labels distributes over the clusters. And now I want to run PCA, so I'm going to say, okay, run PCA on X, right? So I've got PCA. What's supposed to be the size of this? I think we call it P on the board. Let's say P from PCA. So what's the size of this, do you think? What's supposed to be the size of it? Who's this P? Is this matrix, right? Times, I said I multiply with the eigenvectors, with the eigenvalues, square root of them, standard deviations. If I really want the orthonormal matrix, it's just each eigenvector is d dimensions, and I have d of them, so it's a d by d matrix. That's 784 times 784, right? So now, if I want to obtain x in, say, 3 dimensions, I have to do what? Get the original x, then multiply with p, but only with, so I have to use all rows, right? And only the first 3 columns. So if I do this, what's the size now of x? Or of x3? I think I multiply just with 1 column, which is the 3 column. I have to do 1, 2, 3, right? So this is saying, cut this matrix, use all the rows, and only the first 3 columns, 1, 2, 3. Okay, so now what's the size of this? Now I've got my PCA, I have the images represented instead of 784 dimensions in 3 dimensions. So what I'm going to do is to say, okay, run k-means again on this matrix. So now I'm plugging this matrix here. So I want to partition the points. I've done k-means. Now this is not the original matrix. It's the dimensionality reduced matrix in 3D, right? So I could replot these things. I have the indices from the labels. I could say histogram of, instead of y, that's original y from k-means over all data, I do y3. How does this look? Not so good. Why doesn't it look so good? Because I lost information, right? So actually I have the eigenvalues here. If I look at them, I only took the 3 ones, the biggest 3. You can tell I lost all this information that was in the eigenvalues that were not 0. So how about I take 20 of them, right? So I'm projecting the data not in 3 dimensions, but in 20. Okay, let's say x20 here is, I'm only going to take the 20 columns, and then I can write k-means again, right? I'm going to get different cluster IDs because I'm using this matrix that's the PCA in 20 dimensions. So now I can replot this histogram for, this is only for label 7. It's better than the one in 3 dimensions, but not as good as the one with 784 dimensions. How about the label 2s? It's not bad. In 20 dimensions, I think most of these indices, what's the other one that we did? 3. In 20 dimensions, I think the k-means runs reasonably well because the 20 dimensions that are the biggest 20 dimensions of variance, the biggest eigenvalues, contain most of the information on the data. So by removing the other 754 dimensions, I've got a decent representation of the data. I think I can plot here things. So I can plot what happens here. I'm going to plot the x3. I can't plot more than 3 dimensions because I can't see them. So I'm going to use x3. and I'm plotting only the data that has index 5, that is the 5 labels, right? Here's they are. Let's do a hold on here and a grid on. So I'm only plotting the PCA output, but only for the images that have label 5, right? So let's add to that the images that have label 2. And we'll add it with a different color so we can see them, right? So this is a projection in 3 dimensions, so it doesn't have the separation that it has in 784 dimensions or in 20 dimensions. You can't expect things to look so nice. Let's try to add more classes here. How about we add the 7s? Let's add them with blue. 7s are reasonably separated. You can see 3, although it's a projection, it's only 3 dimensions out of 784. The 7s look like white in their own corner, right? Let's add another one. I don't know if I have the 9s maybe. Let's make those, what color should we make them? Black? The 9s don't look that good, I guess. Oh, I think if you know how to rotate this plot to look at it properly, you see all the blacks at the 9s. Turns out that for this image data, even 3 dimensions capture a lot of the variance. We can compute actually how much variance we capture with only 3 dimensions. Turns out 20 dimensions capture 99% of it. That is, we can, by putting it in 20 dimensions, which we cannot plot, it's already, all the algorithms K-means and KNN should start working pretty well on this data set, because in 20 well-designed dimensions like PCA, we'll have all the distances almost like we had it in 784 dimensions. More on this next time. Next time being Wednesday.